this weekend because of this book. And because he invented a very famous magnet. And this author of this book found him by doing research on the internet. And she devoted an entire chapter of this book to John.
Starts on 67.
Starts on page 67. It was an amazing book, and it's about how Washington gave away America's technological secrets to China and other countries, and how we're losing our manufacturing to other countries. And so this conference is all about this topic. And they've invited John to come and speak, and he's going to be getting an award at this conference. And so this is the PowerPoint that he's going to deliver at that conference. So, John.
Dr. Croy, take it away.
Dr. Croy, take it away.
I think he's taking my chair.
Oh.
You.
Watch that growth.
So this talk is only about 15 minutes, so I don't have much time to go into great detail. And I think what they asked me to do was to, they wanted to know why I did what I did. You know, what was the thought behind the research, the genesis of the research that we went into. So to begin, I was introduced to the interesting world of rare earths at the Ames Laboratory, Iowa State University, where I did my graduate work in the Department of Metallurgy. Historically, the Ames Laboratory was part of the chemistry division of the Manhattan Project, which was headed by Dr. Frank Spedding. Spedding was a very, for anybody that studied rare earths, Dr. Spedding was very famous. In fact, he's often referred to as the father of rare earths. The major developments of the chemistry division of the Manhattan Project during the Second World War was they developed the technology for producing metallic uranium and plutonium, which is of course used to make bombs. They also provided roughly half of the uranium for the uranium metal used for their first controlled fission reactor at the University of Chicago, which took place in December 2nd, 1942. Following the World War II, the Ames Laboratory became part of the old Atomic Energy Commission. And at that time, shortly after the end of the Second World War, Dr. Spedding invented the process that he is most famous for, which was the ion exchange process for the separation of rare earths and actinides. And again, for people that know anything about rare earths, this was a big deal because rare earths are very difficult to separate. And so because of this, the Ames Laboratory became the major center for rare earth research in the world. In fact, the only center for rare earth research in the world, because it was the only place where they had large quantities of research grade, high purity research grade rare earths.
John, can I interrupt? You know, I bet these kids don't realize that in order to get something like these rare earths out of the soil, how does that actually happen?
Well,
And think back to the copper mine that we visited.
You're not suggesting I change my talk here now.
No.
If you want me to explain that later.
Just bring it down to Marshall's level.
I can talk about that
The
later.
kids probably don't understand how that happens.
Let's do it later, I agree with John.
Okay.
So, continuing on, I obtained my PhD degree, or did my graduate work in the metallurgy department. I'm involved with the preparation and magnetic properties of very pure, very high purity rare earth metals. So I became somewhat of an authority on rare earths. My major advisor was, in fact, Dr. Frank Spedding. In fact, I was his last PhD student. One of hundreds of PhD students they call his family tree.
Wow.
It's interesting that while I was doing my graduate work, I was very worried about being able to find a job after I left college, because the field of rare earths was so small that I thought I wasn't going to be able to obtain work. However, immediately following my graduation, I was hired by the Magnetic Materials Group, the physics department, General Motors Research Laboratory in Warren, Michigan. And the first thing you might ask is, why is General Motors interested in permanent magnets? And reason for that is in the 1970s, GM was by far the world's largest automobile producer. And automobiles are by far, in fact, by far the largest users of permanent magnets.
Even today?
Yes, they go into all of these applications. Most of them are motors. But if you were to take a luxury automobile, the two front seats on the car will have about 12 motors, something like a dozen motors. These are, they use a fairly low performance magnet called a centered magnet, but, and they still do today. So again, looking back historically, when I arrived at General Motors, the first OPEC oil embargo had occurred in 1973. Some of us in this group can remember that. Some of you are
Yeah.
too young to remember it. But the price of gasoline in the USA soared. Therefore, there was very intense effort in GM and other automotive companies to improve the fuel economy of automobiles. And one way you can improve the fuel economy is, of course, to reduce the weight of the car. And one way to reduce the weight of the car was simply to reduce the weight and size of these motors or these applications on the automobile by using a higher performance magnet. At that time, there was one of the first rare earth applications, which was the samarium cobalt. It was based on an intermetallic compound, samarium cobalt 5, had been discovered, but they were considered far too expensive for automotive use because both samarium and cobalt are relatively expensive. So the mission of the Magnetic Materials Group was to develop a lower cost, higher performance rare earth iron. In other words, we wanted to basically replace the cobalt and hopefully use a different rare earth permanent magnet. However, there was a serious technical problem that had prevented people from doing this for at least several decades. People have been trying to make such a magnet. The problem was the lack of a suitable intermetallic compound like samarium cobalt 5. Permanent magnets, all permanent magnets require an intermetallic compound. And not only the intermetallic compound, first of all, must be ferromagnetic. It has to be magnetically ordered. But then a second requirement is that it has to have uniaxial crystal symmetry, which means it has to be either hexagonal, tetragonal, or rhombohedral, which means that the C-axis has to be longer and have a different energy level than the basal plane axis, which means that you can't use a cubic structure because in this case the C, A, and B axes are all the same.
Is this at the atomic level?
At the crystalline level, not really at the atomic level, but it's hard to explain without going into a lot of detail.
Yeah, but it's still small.
Yes, very small. So it cannot be cubic because there is no energy difference between A, B, and C. There is no magnetic hardening, therefore no coercive force, and therefore you can't make a permanent magnet of it. Oops, I went the wrong way, didn't I?
No, you didn't.
No, I didn't. I went way far.
Oh, skip that.